Hey, let's get started. So yeah, it's Monday again, and it's the Legend of Data. So yeah, I know that I've made some changes because last week I talked about that we would talk about boost algorithms, but I've changed my mind. I've changed it to like how to compare models and like what metrics we should use to compare models. Because I think last week I just realized I've never talked about that. So yeah, so I think it's good to just go through this. I also found a very interesting article on towards data science, which the link will be at the end of the presentation. So yeah, so without further ado, let's get started. So yeah, so we always have these questions like how can we compare which machine learning model is better actually? Um, so do I have a okay? Yeah, I just thought that I have a spelling mistake, but like it must be some like typo somewhere. I'm not so sure, but yeah. So how can we compare which model is better? Because there's always the case that we have to make some fine tuning on models, and we have to sometimes compare which model is better to use to achieve what we want to achieve, right? To do some accurate predictions. So yeah, we have to figure out a way to do that. So um, so we need to have a standard to measure it. We need to have a metrics to measure like whether a model is good or can it be better, or do I make these changes actually make my model better, or if I want to compare the performance of two models, like what should we do? And whether it's like good on training data means good on everything. So I just realized that I haven't really discussed about the last point in the slides a lot. So because I got distracted with with the metric thing. So if I have time, I will elaborate more on the last point at the end of the video. So um, yeah, we need metrics because we need a standard measurement of how good the model is. It's not just because like it's data science, so it needs to be scientific. So like all the experiment that you do in the lab, in the laboratory, that you need to have some measures to, so it's like a standard measure of how good the model is, so we can compare. Without a standard measure, then like it's so difficult. And also sometimes a metrics, a measurement that we use may not be the best one. So that's why it's a topic that I think is quite interesting, and we should really put some thought in it. Um, yeah, so this is scikit-learn, and it provides loads of metrics to use actually. So you can see that accuracy is like the most common thing that we talk about every day. How accurate something is. So it's kind of the most straightforward and what most people would think about when they talk about like whether the model is good. Um, well, these are variation of it. So also there's F1 score, which we come across it after. It kind of involve a concept of precision and recall. So we'll talk about those as well. Um, Other things that is provided by scikit-learn is the ROC. So this is involved in something called the ROC curve that we will also cover. So this is just an overview of everything. So these are more like the classification measures. There are also other things that is used, like for example regression. We would use some, means. Remember we talk about the mean square error, and we do the linear regressions, and also there are other measurements out to. But I think today we're gonna focus on the classification ones, because these are the ones that like involve some like trickiness in it. So yeah, so and also like I said, most problem actually are classification problems to help people make decisions. So yeah, those are the one that's got most interesting things going on. So we gotta focus on that, and also if I have time, I'll also elaborate the training score and the verification testing score and all this stuff. So yeah, because I think I talk a little bit about it in the string test split, but I can elaborate a little bit more on that. But the main focus is still, how to find the right metrics for measuring our classification problems. So these will be the ones that's commonly used: accuracy, precision, and recall, and F1 score. So yeah, we got to talk a little bit about those. So accuracy is, like I said, most straightforward, and most people think about accuracy when they want to measure how good a model is. So it's just like how many labels that it got correctly, or to be more precise, is the percentage of the correct labels, which means that you check all the, it's a classification problem, so you check how many you got right and divided by everything that you have tried to predict. So that's the measurement. So Cyclone provided that, like I showed you before. So this is the method that you can use. So it's in the Cyclone Matrix accuracy score. So what you need is to provide a true label. So this is the correct answer, and your prediction says this is your answer. So it's kind of like examination, right? You check your answer against the model answer. So how many you got right. And you can also have an option to normalize it or not. So it's capturing the percentage or not, or like just the number of how many you got right. So yeah, this is the most straightforward, and this is the most well-known one because, well, it's really like an examination, that how many you got right. So that's very straightforward. So yeah, so this saying that if normalized is true, they will return the fraction, which if you multiply by 100, it will be the percentage, and if not, that would just be like the number that you got right. Yeah, normalized equals to true. And yeah, so, and right, so you can see that this is an example here that is quite you know simple. So only like 4 labels, like 4 questions, and 2 of them is right. So, well, it's 2 is 0.5%, 2 4 is 0.5%, and the correct will be like 2 questions you answer correctly. Yeah, so that's it. Nothing very complicated here with the accuracy, but there's a catches here. So accuracy sometimes not a very good measurement because I will show you why it's not a good measurement. We have a typical example here. For example, I want to identify the terrorist trying to board a flight. So um, so I can say that anyone can provide a model with greater than 99% accuracy. This is this is much better than like most machine learning models. Like for a very good machine learning models, it would be like close to 90%, and anything greater than 70% is decent, I would say. But not, people usually want it to be 80 to 90% accurate. Greater than 90% is really good. Sometimes you have to be really careful, like how you get the greater than 90%. For example, if you're overfitting it, so that's involved with the things I got to talk about with the train test splits. That if you, for example, you get a really good score in your training set, like greater than 90%, then it's probably that maybe you're overfitting the data, so you have to check it against the test set, right? So you have to check whether it's doing good in general or it's just doing good on the training data. So this is like the overfitting and underfitting kind of things. Yeah, now I feel bad that I forgot to put some slides in it, but I may not have time to cover it. But otherwise, I'll just like improvise and put those in the slides afterwards. So also like well, how can we achieve that? So I would be like, well, this is actually very easy. We call that like constant prediction, and a lot of models like this would we have this problem. So I've encountered things like this before. It's like I would talk about why this is the case, but yeah, usually if you train a model to do that, and the problem is that you would get a model very good, greater than 99% accuracy. It's like, ooh, wow, like, but you have a feeling that something is wrong, and then you check the prediction. It's like all of them would be the same. So it's a constant prediction. For example, in this case, then the model is basically predict that everybody is not a terrorist. So what's going on here? Um, so because the data here is that well, there are many 800 million like passengers. It's actually like flying in the U.S., but only 19 confirmed terrorists. So only 19 terrorists got caught. So you can see the accuracy is like 99, because like the reason being, like, it's so rare to have a terrorist boarding a plane. So yeah, so this is from the blog that I talk about, so you should read that afterwards. So the reason why this problem happened is that most of it is because the data is imbalanced, which means that, for example, in this classification problems, like one class is like the occasion of it happening is like very, very low, so the data is imbalanced. Um, so when you try to look at the accuracy of it, so a constant prediction actually would give a very good accuracy, because the chances of the others. So if you predict everything to be the majority, so um, actually the chances of you getting that right is actually quite high, because the chances of, so like it's like I'm predicting that if I got like if I win a lottery, actually every day if I bought a lottery, if I predict myself to not win that lottery, is actually quite high, because it's quite rare to win a lottery. So yeah, so that's how why the problem is happening. And sometimes not good, because we do care if we guess it wrong. For example, in this case, like, we actually want something to do better than a constant prediction, because we really want to catch this terrorist. We would rather keep someone that doesn't is suspicious, to not board the plane, and have a more like a thorough check before letting that person board the plane, rather than letting suspicious people to board the plane, because the stake is quite high. If anything happen, if there's an attack, then we would lose many lives. So yeah, the stake of making mistake is quite high. So we don't want to just look at the accuracy. We want to be more safe. This also happened to, like, for example, medical examination. That if we want to be sure that someone is is having, like, let's say, a tumor, that, like, whether it's a cancer or not, then we want to be sure that it is definitely not a cancer, to let that person to go home without any treatment, because if that's a cancer, then that would cost someone's life without treating them correctly, right? So that's another example. So sometimes we would rather sacrifice of, like, having some false positive than letting there is some false negative. So I'll talk about this false positive, false negative in a bit. Um, so so yeah, sometimes, like, we want to identify the positive cases, these minority cases. We want to pick them out. We can't just let this slip through. So what should we do? Um, so actually, we have other measurements of measuring how good or bad this model is. It's called a precision and recall measurement. So for example, the recall is actually the model's ability of finding the the um, the positives in this case. So this is like the true positive over the true positive plus the true negative. So true positives are the correctly labeled positives. So for example, in this terrorist case, so if the terrorist is labeled as 1, which is the positive, then a true positive is that a terrorist is correctly labeled, correctly identified. So false negatives are actually the terrorists that got away. So they are labeled as a negative, but they're actually positive. So these would be, in this case, would be the terrorists that got away with it. So as you can see that in the blog that also mentions, if you kind of records the way that, like, you how much you let this positive to slip by. So you can actually label everything as positive, and you get a perfect score in the recall. So because if you label everyone as the terrorist, including those 19 confirmed terrorists, then you have 19 correctly identified terrorists, and it will be over 19 plus. So none of them get away, right? Because everybody is a terrorist. So 19 over 19, so you get a score 1 for recall, which is the highest score that a recall can get. So, but that is that helpful? Well, that's still not helpful. That's, again, it's a constant prediction, and it's not reflecting the truth. So the problem with that is that it will have actually a very low precision. So basically, recall is like how much I I catch those positive, right? So I catch all of them, but the precision is very low because I have a lot of mistakes. So the precision is actually true positive over true positive plus false positive. So it's like, so false positive are the ones that is supposed to be negative, but you label them as positive. So it's the one that you just you just label everything, right? Oh, there's a very good meme in circulating. Oh, I forgot to put it there. See if I can find it afterwards. That's like the precision and recall that like is super funny. It's about doctor, saying that whether someone got pregnant or something. Okay, so in this case, the terrorist case, so true positive. Of course, this the terrorist that we found, those 19 terrorists. But now the denominator would be like including everybody that was incorrectly labeled as terrorist. That would be everybody else. So then you get a super low score in this case. So we don't want that. So we need to actually so this said that like recall express the ability to find, so it's like how many of them you can catch, but precision express like uh, out of that, like how precise you are. Like if you get, you know, if the 19, you caught 19 terrorists and all of them are terrorists, then you got a perfect score for this precision here, because none of them is like mislabeled. So yeah. Okay, let me see if I can find that funny picture. And okay, so this is the precision and recall doctor meme. If I can find it, is it this one? Oops, no, it's yeah. Let me see if I can find it. Is Yeah. Oh, it's yeah. I've seen it once, like in circle. Oh, it's this one. Yes, this one. Can I make it super big, please? Oops. Oh, why is it like this? Okay. Let me see if I can. Okay, so this picture. So yeah, false positive and false negative here. So it's not precision and recall. But it's involved in calculating the precision and recall. So false positive is actually like, yes, the doctor is telling the man that like you're pregnant, which well, it's obviously false positive because, well, biological men can't get pregnant, and yeah, the other is like, obviously this woman is pregnant and the doctor is saying that you're not pregnant. This is quite funny. I don't know whether I can borrow this image and put it somewhere. Yeah, so let me see. Sorry, I don't like I don't like editing it like during the streaming, but I really, oops, oh sorry. Yeah, but I really forgot about this, and yeah, I'm just quickly do this. Yep. Yeah, cause like I feel like I usually kind of remember things when I was talking about it. So that's like, have you heard about the rubber duck debugging? So basically, programmer talks to a rubber duck, or rubber duck programming, like how, when they talk to a rubber duck, that they would find like all the problems and know how to debug, because they are actually talking to something. So if you say it out loud, then it's easier to, clear your thoughts and things like that. So I feel like the same. Like every time I do streaming, I feel like, oh, I forgot to do this, and yeah. So now you got this funny picture, there. Okay. I should also put the link of this actually. Yeah, this actually may be useful. I would put the link here as well. Sorry, just one sec. Let me go back to. Oops. Yeah. Yeah. So yeah, I feel so sorry about that. Like usually I just like finish the slides and I'll be like, okay, I'm good. But and then I was like, oh, when I started, then I'll be like, I forgot to put something in it. So yeah, this is how it is. So just put this higher. Yeah, and I really like using slides.com because, well, I'm I'm used to it maybe, but I feel like I could do it very quickly. Okay, so and so this is precision and recall. So what I'm going to talk about is that in Scikit-learn you can also do this precision and recall measurements easily because it's provided here. I just put the link there so you can basically check it out, but there's nothing very interesting. It's just like other Scikit-learn APIs that you created the class there, the precision score. It's the same with recall actually, and you just need to provide like the label, like the correct answer and your answer, so how good you're doing, and also the label, so you can also say it's like, is it a binary or something. Yeah, and then it would just like give you all these measurements. So is it a binary, or there's other like weighted measurements or samples? So yeah, there are a lot of things you can control. Um, so all these measurement actually is you you realize that all these measurement actually needs you. The one thing, the only one problem, okay, that's the precision and recall is doing during training a model is that it won't you can't calculate them on the go. What I mean is that you have to give in, like you have to give all these all this you have to finalize your conclusions at the end because you have to add them up, right? So this is a overview, the picture of all your data. So the problem would be if you're training a model, you put in the training data one by one, so it doesn't make a conclusion that is conclusive because how precision and recalls are calculated, it need to have all the true positive and true negative, like or false negatives, to be in the equations to be calculated. So yeah, so this like false positive and like false negative. So these are the ones that need to be in the picture. So if you are putting in training data one by one, so you have to have a whole picture of it. So what you can for example, if you just like oh, so far I've trained like, let's say 10 data point, and then just use that 10 data point to calculate, it's not accurate how good it is. So mainly they will be used to evaluate a model rather than used to fine-tune the training or something like that. So yeah. Okay, so F1 score is actually a combined measurement of both. So you can see the formula is like this. Um, well, I can't explain why like someone come up with this. I don't know what, but like you can see that the characteristic of it is that it was still remain the 0 and 1 range, because if precision or recall is very bad, it's because precision and recall are in the 0 and 1 range, right? So if recall is very bad, it's zeros, and you can see the F1 score with 0. If precision is 0, it will also be 0. And if both of them are good, so 1 and 1 and 1 and 1 here, so there's a 2, that's why there's a 2 there. To cancel out the denominator, which is so the best F1 score you can get is 1. So yeah, the reason why it is like this is that you because it's the product of precision and recall. So you can't have one very good and the one very bad, because it would also make the score very low. So you have to have both that is performing well, and then it just kind of so the denominator and the 2 there is kind of just to maintain the range of the calculate of the F1 score. So Scikit-learn also have this, like everything else. So yeah, you can always go and check it. So it's very similar API again. It's like the precision and recalls. I also get different calculations, but it will return an F1 score for you. I think this one will be more useful than the precision and recall, because because the F1 score is quite complicated here, right? So you can't just count all the positive and negative and true positive, true negative, and all this, like, and to easily calculate it, you have to so having a using this is actually quite nice. So another thing is the confusion matrix. So confusion matrix. What it is basically having the true positive, false negative, true negative laid down in a matrix for you, right? So So yeah, it's just like 4 numbers that we care about, and it's all laid down in kind of like a matrix format. Cyclone also have it. Well, like what Cyclone doesn't have, I really want to know. Um, so it would. So the difference is that it would give an array that will give you those 4 numbers. Yeah, or there will be like more than that if it's like a multiple class. Instead of 2 classes, then it will have that. So for example, this you can see it as a confusion matrix with is 3 by 3 because you have 3 classes. So yeah, so it's like it's supposed to be an and. No, so it's supposed to be a cat, but it's labeled as an and. So that would be cat, bird, and cat. So this one you can see that um, there's 2 ends identified correctly. You can see here, and cat is like there's 2 cats identified correctly, but there is yeah, 1 cat that is identified as an ant, and 1 bird is identified as a cat here. So yeah. Um, yeah, so if it's like so if it's like the one that we had in the slide, so it's just like true and false, then you would have you can actually it will be 2 by 2, and then this is here just like yeah, just flatten it like this. So you get the true negative, false positive, false negative, and true positive here. Okay. Right. This is Cyclone, and the rock curve or rock curve is slightly more complicated than the confusion matrix because actually it is calculating the rate. Okay, so and so remember, like we have the prediction probability, right? So actually there's an example somewhere here. Do I want to show it now? Maybe later. So this is the typical rock curve. So you can see that usually the curve will be like this blue and the red line. Um, so the black line there is a reference. It's a reference of a random guess. Okay, so so basically, so what this is plotting is that we can calculate for each model. We can calculate the true positive rate here with a different threshold. So with the same model, and remember we have the prediction probability, like how sure you are this is a positive. So we can change that. We can change that like, oh, it's only a positive when it's greater than 80%. Like only if you're 80% certain that it's the true positive. So yeah, so you can actually change those rate. Okay, so there's a rate that you can change. So it's the same formula of like how you calculate the so this the precision here, and this is recall here. So true. No, it's not. Okay, so it's not. It's slightly different. So okay, compared to the previous one, then like yeah, false negative, this false positive, but those are different. So yeah, it's more complicated here. So this is the true positive, so this is the same. So true positive plus false negative. So this is the same as precision. But this false positive rate, so true positive rate is actually precision. False positive rate is actually the false version of it. So just replace all the true here. Like true become false, false become true. So it's the reverse of it. So there's a name for this. So this is called precision. This is maybe the false precision. I don't know how do you call that, but like you just flip the true and the false here in this formula, and it'll become this. So yeah, you change the threshold of how certain you are, and then you would have different rate here, and then you just plot them. So this is the random guess. So your precision is as good as your false positive rate because it's random. So it's always stay the same. So because so the because it's a random guess, so the rate that you get it right and the rate that you get it wrong basically stay the same, stay proportional, because there's no difference between the true and the false, right? Because you're just randomly like flipping a coin, so it doesn't matter. So that's why is they are always the same. So that's why it's a straight line. But if your model is doing some prediction, it has an opinion about whether it's a true and false, it should get a curve like the blue and the red line. if you got a line that is below the lower triangle there, so it's kind of like, so what does that mean? That means that you probably flip the truth and the false wrong. So if you flip the true and the false, so sometimes maybe you label it wrong, or like you forgot to flip it over for whatever reason, then it would get a curve that's below that straight line. So if that happened, you know that you have to flip the truth and the false. Maybe you made a mistake somewhere, try to debug it. So yeah, that's the rock curve. So yeah, for rock curve, you can do more research about it. You can read the article that I suggested as well. It will also explain a little bit. Um, but basically, you want a rock curve that is as close to as close as the box. So the blue one is actually better than the red one. Let's put it this way. So you want something that is, maybe even better than blue one. So it's like higher than the blue one. So you want something like that, which means that you get, you can find the true positive very easily uh, by not sacrificing having a lot of false positive. Okay, so um, yeah, we can have a look at this scikit-learn thing. I'm thinking about like doing some comparison myself in the I don't know whether what should I do now, because like I'm thinking about I will really need to talk about the training accuracy versus the training score versus the testing score and things like that. But yeah, because I don't know why I missed I missed that bit. I was too into this thing. So let's see like how far I can go. Okay, so this is the scikit-learn metrics. So this is the rock curve. So basically what it returns these values for you. So the false positive rate and the true positive rate, and it would be an array that got returns, and yeah, so score greater than the thresholds. Um, yeah, actually you can use it to plot a graph. So this is what we gotta look at actually. So you can see that yeah, here's the usage. This is too complicated. I plan to like do a simpler version of this, so that's why I have my Jupyter notebook open somewhere, and we gotta do that. So you can see that for the rock curve, then actually we get two things returned. So it's like the false positive rate and the true positive rate, and then you can just plot them one against each other, so you get the rock curve. So let me grab this snippet, and yeah, and I would make a simpler version of this um, for them. And yeah, so I gotta create a new file, and this gonna be an yeah. So let me put it here. And so what I've got to do now is that I gotta simplify it, because I don't want to compare that many things. So I would remove this pipeline because I want to do that. And so random tree embeddings, I'm not going to do that. And I'm going to use random forest classifier. Yes, so I gotta use it. I'm not going to one hot encoder. So what this is doing here, yeah, I'm not so sure why this is a random. Maybe it's a pipeline thingy going on here. Dot transform dot apply logistic regression. Okay, right. So yeah, this is doing like the so this is the random forest with the linear regression there. Okay, so this is it's using the gradient boots. Okay, and then it would, so yeah, you can see that it's both doing the prediction probability here. Okay, so I think because they're plotting something afterwards, which we'll see in a bit. And okay, so this is just using the gradient, And this is the logistic regression one, so that's why they do the one hot encoding and do the logistic regression. So I think what I gotta do is like I'm not going to do this logistic regression, so I gotta delete this one that is involving this, and yeah, so I just gotta keep it simple. So I just gotta do a gradient boost classification. Same as this one, I will just do a random forest classification here. So I'm not going to feed these things. So not this one as well. Just got to do a simple random forest here. So all the predictions are done here, so I don't need this one. Okay. So now it's super simple. So we have random forest classification here. That let me make it bigger. So I fit it, and then for the random boost thing, I would fit it. So after that, I'll do a prediction of the probability here. I will have the test set. So yeah, the string test split is done here. But actually, we don't need this. We only need this one because I'm not using sum of trees. I'm not using this one here. Okay. So yeah. So what we are doing here is that we generate this classification problem with all this simple sample size here. Then we'll split them into train test split. We'd have random forest. So we have 10 classes actually. So well, this is a big one. I could actually make it 2, I think. Let's see. They're fitted, and so the same with the gradient boost, so we can compare them. And then this is actually plotting the whole thing, but I don't want to plot everything because these ones I don't have right now. So I only have the random forest one, so I gotta skip this one and also this one. So I just gotta keep the random forest and the gradient boost. So these two are actually from the ROC curve that's generated. So I have the true positive rate, false positive rate, same as this one, and the label here is done, and ROC curve. This is the title and legend. To show the graphs, same as this one. I gotta so what is it doing here? This one is different. So this is the second figure. So okay, so this is zoom in. Okay, I gotta just do the same treatment for this one. Right, and let's try this. Okay. Right, so you can compare that how these two are doing. So it seems like the gradient boost is doing better in this case here. Sorry, the dark theme make it super weird, but yeah, you can actually like download this notebook afterwards and play it yourself. Um, this is very strange, like for the gradient boosting. So it's zoom in here at this area here. Okay, so yeah, it's just like slightly better than the random forest. So yeah, this is how you compare different models. And also you can calculate other things. Like I said, you can calculate accuracy, and you can also calculate the precision and the recall. So let's see if I can do that. So I have these predictions. Okay, more predictions of that. So um, remember we have, if we want to calculate the accuracy, so we need to put in the true and the predict, right? So what I'm going to do is that I am going to plot so oops. So this is, let me put a label there. Okay, so this one is the ROC curve. Right, so this is a ROC curve, and actually I want to have a this will be the accuracy. Yeah, I'm like accuracy score. Uh, Score, right? Okay, so down I have this, and then I would have Actually, this is okay. I have to split the cell because I need the prediction, and yeah, this is doing the rock curve here. So what I'm going to do is that, yeah. So what I am going to do, actually, okay, I'll do this after because yeah, because this I don't want to break this nicely organized code. Just gonna put it here. So sorry, I got a cough because I got something in my throat. Yeah. So now what I gotta do is I gotta calculate accuracy. So I gotta import. Yeah, I gotta import the accuracy scored, and I gotta compare these two. So what I gotta do is type print. Random forest, and then this would be so I gotta use the accuracy scored, and then maybe I just put it in the same sentence here because there's no point of maybe I can f accuracy equals 2. So I have the it will be like the y test and the prediction. Yeah, so this is prediction probability. So I probably need just a prediction. So what I gotta do is that I gotta do this, and this would be the gradient prediction. Yeah. Okay, and let me have a look. Yeah, why they changed the order? This is super strange. I hope. Yeah. Right. So I have to change it to just predict. And I have the right roof, and I'll have the actually I'll have the predict out f here. So and now I have another one for the gradient boosting. Right, so this one would be this here. And then I gotta print the other one as well. I just like use GRD for now. I'm just too lazy. Right. Oops. Huh. Too many indexes. Did I put something wrong in there? Oh yeah, to be like test, y test. And then, yeah. Huh. Yeah, it's the Cyclone index thing again. So I think because maybe the prediction output is not the same. So yeah. Okay. So yeah, you can see the accuracy is quite high, but also the gradient boosting is doing slightly better than the random forest. So yeah, that's that. And also we can calculate the precision and recall. So we just need to do that. So a precision score. So it's basically the same thing, right? So we just import it, and then go here. So this is precision score, and I would have my thing here, and so basically it would be the same thing. I don't even have to predict it again. So oops, this one would be the precision score. Pre, and then this will be pre. So precision. Right, so it's also not bad, but the precision for the random forest is slightly better. So yeah, so you can see that like sometimes it depends on what you care about. You may have to choose different algorithm. So for a task that maybe the precision is more important than accuracy, then maybe you want to choose the other one. So you can see this is a good example of showing that sometimes doing good on accuracy doesn't mean that I do very good on precision, and sometimes you so like whether this model is better than the other one actually just based on what metrics you care about. You can do the same with record, but I'm not going to do it here now. So I gotta just save it here. And I think the rest of the time I can talk a little bit about like maybe the train test, you know, overfitting and yeah underfitting. So what I'm gonna do is so maybe uh, so basically, where should I start? So it's so difficult when I'm not prepared. So over fitting vs under fitting, or sometimes it's called there's another term for that. Sometimes it's called uh, oh bias and oh I'm so bad with names. Um, uh, Bias and what's that called? And yeah, so it's variance. Yes, yeah. Sorry, I'm so bad with names. Like I got that's my problem with interviews because like I can say that overfitting and underfitting is very easy to remember, and then this bias and variance is it for me it's like someone's name is so random like that is so difficult to remember. So okay, so bias is actually means that it is made by the model to make the target function variance amount change given the training data. So variance is how much it would change given the different training data. So variance is actually vulnerable to. Do you have a picture actually? Yeah, so you can see that. Oops. Whoa. Okay. So okay, this is a very good picture, and I'm opening that right now. So yeah, yeah, you can find all this information in like in the internet very easily because a lot of data science information there. So you can see that like overfitting is high variance, and so underfitting is high bias. So how I remember them before, of course, I'm not very good at remembering names, like I said, but also those terms doesn't like mean anything. I think because like maybe it's my English thing as well that like so I don't get the context of it. I don't, you know what I mean? Like so okay, high variance means that it changes a lot. So it's overfitting. So well, basically you change the model. The model like trick itself so much that it fits all the data very perfectly. So it fits all the training data perfectly. But that means that it's not general enough. That is, for example, like this one is well for human eyes, it look like a curve like this, right? So, but you know, if we try to tweak it too much with too much variance, then it would basically, you know, it's perfect, but it's not. If I have a new data point that's like somewhere in this belt, then basically you have to change the model to fit it, which is not good. High bias, I don't know why it names high bias. That's why I always like trip over it. And so it's underfitting means that it hasn't got changed enough. That basically the training data is not even good enough to explain anything. So for example, well this little curve and this line basically doesn't match in human eyes. So it just means that the model basically doesn't look at the data that well. That it doesn't fit even the training data that well. So usually what happens is that for this one, so this one will have a low uh, training score. So it will be this one, okay? So yeah, I'm just like talking and doing it on the go. Right. So for this one, what happened with the overfitting was that it will have a high training score, but it will get a low testing score. So for the underfitting, it's bad anyway. So like you don't even want to look at the testing score. It won't be good. So yeah, no testing score. So the ideal that we want, is of course like both would be high. So it would be a high training score. It could be slightly lower than the overfitting one, but it also got a high testing score because it's general good enough that if I have a point kind of near this spout, it would kind of still have a reasonable error. So yeah, so this is generally like the overfitting and underfitting. That's why having a train test split is important because then you have two scores to give you an idea of the whole picture of what's going on. If you just look at the training score, basically you may think this overfitted model is better, right? But because this good balanced model actually may have a lower training score than the overfitted model. So that's why we have to also look at the testing score. So sometimes you even want to break it more than two sets, your data. You want to break it into more sets because you may want to use some data to fine tune your model, and then you don't want to use your final testing data to do that because all the testing data should be only used once. So you have some the so, some extra data that preserve to just do some the tweaking of your model. So that's the training set, test set, and the variation set. So those are the variation data that you use to fine tune your model. So yeah, I think that's it for me today. Sorry that like I was so carried away and not. I'm not a very organized person, if you don't know already. So yeah, sometimes this happened, and I was like carried away with talking about something, and said, oh, I forgot that I should also talk about that. So sorry about that. And so yeah, next time I would really talk about boosting algorithms, different boosting algorithms, and like maybe I would talk a little bit more about algorithms in general, like the common ones that what's the difference, when to use them, and things like that. So yeah, so I think that's it from me, and I will see you on Wednesday or meet me pie. So bye.